to describe. So now we're going to do a little derivation of the Lambertian limit. I keep threatening to write this up and publish it someday because the original papers did something about density of states within semiconductors and index of refraction, those kinds of stuff. And I always like the idea of just like imagining light striking and just tracing out the power of each of these rays as they bounce back and forth and doing a more sort of direct calculation of that. So that's what this following little tutorial is going to be. It's just going to be a little hand wavy. We're not going to do too much on each of these steps, but just to give you a rough sense of the outline that's happening. So what you do is you imagine a slab of material and it's bumpy at the top and bottom, meaning you have perfect diffuse scattering when the light comes in and strikes. So there's an anti-reflective coating, meaning there's no reflections up here, and then diffuse scattering down here. So I don't know if you're familiar with the distinction between specular versus diffuse scattering. So specular reflection is what happens when you shine light on like a mirror, and you would see a perfect mirror image of being reflected back. So what that means is, say, a laser beam comes and strikes here, and the angle of incidence would equal the angle of reflection. Diffuse reflection is what happens when a laser beam comes in. Instead of perfectly reflecting in a single direction, it just kind of scatters every which way. And any sort of given surface will be somewhere on that spectrum between being perfectly diffuse versus perfectly specular, or some sort of match in between. So you'll have sort of glossy surfaces where you would be describing as specular. Rough surfaces like the wall there are diffuse. So it turns out a diffuse reflection follows a cosine theta dependence here. We'll kind of talk about that there. So you imagine light comes in, it hits this bumpy surface. All that energy gets redirected every which way. And a perfectly diffuse scatter will be this 4 cosine theta on the directivity of that light. So you notice it means you have a maximum amount of light being going straight, and it'll kind of go to 0 in the horizontal direction, but it'll sort of decay as this cosine. So the idea is if I take the volume under this over a full hemisphere, I should get a value of 1, right? So 1 watt goes in, that watt will be sort of distributed among that dome with some directions being preferred over others. So a perfect scattering, perfectly diffuse surface is also called a Lambertian surface. So Lambertian scattering, say. So then what you do is you just imagine this little ray is like a tiny little infinitesimal laser beam. It's going to propagate from top to bottom along this particular pathway. I'm just going to calculate the attenuation of that energy. How much of that is absorbed in the material? And then you're just going to integrate over this entire thing. So you get this big, horrible integral that looks like this. So you notice the absorption factor is going to be, you're weighing by the directivity here. This is the 1 minus the transmission. So that's your absorption factor for, say, this particular ray here. And then this is the differential surface area representing the Jacobian and spherical coordinates, essentially. And so you notice how we're integrating from 0 to pi over 2, so it's 0 to pi 2, and then you spin it around, adding up the total absorption of each and every ray over that entire thing, this integral. Then you do some hand wave approximations because this is a monster that does not have a closed form solution. So what you usually do is you assume, because we only care about this situation when it's a low loss and thin film. Because if it was very high loss, we wouldn't care. It just absorbs the energy on the first pass. But we are interested in this realm where it's very low loss and it's taking many, many bounces before it finally absorbs energy. So what you do is you assume this product, that alpha times W, is very small. You do a little bit of a Taylor series approximation on this E term. You wave your hands at the integral, and eventually you find that it's actually a pretty straightforward result. Your absorption factor is about 2W. So that represents the fraction of energy that gets absorbed on that first pass. And then what happens is you imagine a ray striking the bottom here, and some of that energy is going to leak out the bottom because I still have this kind of escape cone where some light can escape. We're going to kind of skip the argument for that because this is actually next lecture on Thursday. We're going to talk about this idea of light extraction efficiency. So there's a derivation you can show where it's basically the sine squared of the escape cone is the fraction of light that will be. So never mind that we're just going to pull that by magic, and then you calculate the escape cone, which is using the Snell's law. You find that the light extraction efficiency is 1 over n squared. Okay, so the higher the index of refraction, the narrower that little escape cone gets, which means the less likely there is probability of that ray escaping when it strikes the surface here. So then what you do is you say, okay, now I lose some energy here. How much is now going to reflect back up? And you get this R factor, this reflectance. So that is the light that's absorbed, and then this is the light extraction fraction at left and bottom. This term here is basically 0 though, so you do some hand waving. And then you just repeat in an infinite series. So you're adding up the total energy that gets absorbed and lost with each little bounce. And you finally get a very simple expression, 2 alpha n squared W. So that's the absorption factor. Then what you do is you plug that back into the natural log equivalent path length term, do more hand wavy approximations, and you get this, the equivalent path length is 4n squared times W. So the idea, if this is a slab of silicon, it's 1 micron thick, and I do perfect Lambertian scattering. The index of refraction is about 3.5, so it will behave as if it's about 50 times thicker than it really is. That's sort of this idea. So 1 micron slab of silicon can, in principle, trap the equivalent energy of a 50 micron slab of silicon when you do all this light bouncing. That's the idea. So sometimes it's called the Yablonovich limit, the 4n squared limit. But it gives you a nice hard stake in the ground. This is about the best you can do in terms of path length enhancement. And when you're doing a wide spectrum. So now, interesting fact is a lot of these arguments assume that light is coming in from a single source like the sun. Like, if I'm doing that though, you can see that it's technically possible to cheat the system a little bit, right? So this is a fun thought experiment that says, what if I just put like a big lens, say, on top of my solar cell? I try and concentrate it into this tiny little funnel here, and then cover the rest with metal. So you can see now I don't have to worry with all that surface bumping, and light will very likely just sort of bounce around forever. Very little chance of escape. In fact, the more I concentrate, the better light trapping I can get. So this is the part where I like to open up to the floor, because a thing that will happen a lot in your careers is you're going to have some coworker or boss who's going to throw a wild and crazy idea like this at you, and your job will be to tell them how it sounds like a great idea, but it's really stupid and terrible, and you should never do it. So this is why I like to throw this out. Say, what would be something? Is it a good idea or a bad idea, or what could possibly go wrong? Feel free to just chime in with whatever crazy thoughts you have. Nothing? Okay, we got some. Heat. So that's one issue, is all that light concentrating down here. How many of you have ever tried to burn an ant to death using a magnifying lens? You're going to get a lot of heat, and heat is probably bad for your recombination loss here. So that's one thought. Anything else? I mean, you don't want to just set this thing on fire. But hypothetically, I have really great light absorption. Like I have an anti-reflective coating, so a lot of energy is making its way in. So maybe that's not the worst in the world. Yeah. So you will get sort of a localized hotspot, but all your longer wavelengths, remember, they need like tens of microns. So that'll be kind of true. That may or may not affect things. But I'm getting really great light trapping efficiency, right? Any other practical issues jumping out? What if the sun moves? Right? This only works if I point this at the sun. And if you wait around 5 minutes, the sun will not be here. It'll be over there, which means the only way this could conceivably work is I now have to track the sun. Okay? And in fact, the tighter that beam is and the stronger that lens is, the more unforgiving it will be on my misalignment, say, right? So now you can imagine I need these big giant struts here to hold this up, and this whole contraption is big and heavy, and it has to follow the sun. So that's what I think is one of the major deal breakers, because tracking the sun is going to be very, very hard because you need like these X and Y positions here. The class itself is big and heavy, say. That may not be the best. Maybe there's ways around. You can see like there are just certain practical things that have to get over in order for something like this. But definitely, like if I can just have a solar panel that sits there versus one that follows the sun, it has to change, remember, because the seasons go by, the sun's going to be different. So I have to have like really good, precise positioning. So you can see how that can add up your expenses very, very quickly. Another thing I like to point out is, remember, in principle, we go back here, if I just make my solar cell bumpy, I can get about 80% light trapping efficiency at this, technically. So that means I can either just make my solar cell bumpy, get about 80% of the way there, or I can use this big, horrible, convoluted contraption and maybe get 20% more than that. So there's a nice sort of diminishing. Yeah, technically, you could invest in that. And you might get, instead of 25% efficiency, you'll get 27% efficiency with that extra little bit. So you can see how you're like multiplying your cost by a factor of 10 in exchange for a 20% margin, say, in improvements, right? So those are some ways to think about this sort of scheme. So it's a fun thought experiment. Like, it technically can work, but you can see how, practically speaking, a lot of craziness will add up. So yeah, so alignment, of course, is a big deal. I replicated the slide. So that, and of course, how is this better than just the simple solution that I've already got? Right? So this is easy to do. You just make your back contact rough and bumpy, as opposed to these big giant clumps. So that's a fun sort of thought. Any questions? Comments? Anybody in the online chat have questions? If not, you are now officially all experts in the magical, wonderful world of light trapping.
Great, thanks, James. I don't see any questions in chat either. So Wes asked, can you show the previous slide for 2 minutes?
Oh, this slide here? Or is it the other one here? Oh, and that's another fun thought, is what if I just make this, instead of 1 micron thick, I just make it 2 microns thick. So all these numbers were referenced against a 1 micron solar cell. So if you go to 2, that now means my path length will go to like 100 microns. So that might bump like 90% even. So that's another kind of alternative to think about. I can make it bumpy and just add a few extra micrometers to my thickness.
I think he's asking me about the previous slide also, James.
You mean like this one here, or this guy here? There, I don't need to see the chat.
Yeah, I think it's the one after this one. The next one, yeah.
There you go. Yeah, the problem of alignment. So if I have a lens that's focusing, if the sun sort of moves, and the focal point also. So yeah, that idea of the Lambertian it kind of assumes unconcentrated light. So if I concentrate my light, you can technically, in principle, get better light trapping efficiency. It's just usually not discussed because concentration implies this big, horrible lens thing that makes your life just mechanically difficult. So even though that 4n squared limit is not technically the best you can do, it's sort of treated as a practical effort. Yeah, I think you can show mathematically that if you concentrate the light, that it's coming from like a point source, then you factor it by a sine theta, a 1 over sine theta kind of term, where theta is the angular extent of the thing you're concentrating. So for example, that 4n squared, you imagine, say, a point source hypothetically trap the light infinitely, so you get this 1 over sine theta. So if it's something like the sun, it's something like, it's like a half a degree in width there. So that implies you can multiply even further. But again, that is kind of sort of known in the literature, but not talked about so much because it's just sort of like, well, nobody wants to go down that road. So it's a fun thing where, yeah.
I was just going to say, James, there's a question in the chat from Sawais. It's asking if it's unconcentrated light, then why is the picture showing it is getting concentrated on one point, and what happens after the light is being shown? Actually, Sawais, I don't understand your question, so maybe you may want to speak.
I think the idea is for concentrated light, I'm kind of assuming the light's falling in, say at normal incidence here. Hypothetically, if I had an ideal anti-reflective coating, that light could be coming from all sorts of different directions, and the same argument would still apply. So you imagine, say, it's coming off from 45 degrees, or it's a large bright surface kind of distributed over a large solid angle. Light could be coming in from all directions. But the argument still kind of applies in the sense that once it goes through the ARC and hits this diffuse scatterer, all that back and forth bouncing now applies. But if I concentrate, then the argument says I can use a contraption kind of like this, and the more concentrated it is, the more I can hypothetically focus to this tiny little point, and my light trapping can get exploited even further. That's sort of the argument as I understand it. I think that might answer the question.
Yeah, so always feel free to speak if it was not clear.
Hi. Basically, I was trying to ask, like, as in the on the slide, it is written the light is unconcentrated, but by the diagram, it shows that light is meeting at one point. It means like it is getting concentrated. So I was getting confused by that. And what happens after the light, like according to the diagram, it is getting concentrated. What is happening after that?
After that?
Yeah.
So here is, you're still concentrating, but the point source that you're concentrating from moved over a little bit. So this is the idea of the sun will kind of drift the angle of the sky. So it's coming in the direction and you lose the focal point. But if your light source is distributed over a very large solid angle, then that means you can imagine you don't just have rays coming in from a single direction, they're kind of coming from a handful of different directions. And so that kind of places a lower limit to how much you can focus the light, like that. A lower limit to the, or upper limit, I should say, to the spot size. Sorry, a lower limit. So the sun is not a perfect point source, is kind of the idea. But hypothetically, if the sun were like distributed across the entire sky, then these arguments change. Like a lot of these arguments would change if you were on, say, the surface of Mercury. The sun is like 5 times bigger in the sky now. That would affect your ability to concentrate light using something like this. But it would also mean that if we go back to, say, this picture here, you wouldn't have light coming from a tiny little source of the sky. It'd be this huge sort of distribution from various directions. So these things come into play. They're interesting factors, but it's the sort of thing, it only matters if you're not on Earth. It's kind of the way it works. But it's interesting to think about. There are no other questions. Yes.
Okay.
Thank you for watching.
Yeah. Thanks, James. So we'll see you on Thursday. Okay. And I'll post the recorded video. Right. Thank you all.
Okay. All right. Take care. Thanks for dropping in.
Bye-bye.